Okay, I got a question very similar to this example that I've written on the screen from a student. They are having a little bit of difficulty. The directions are asking that we write this number as a complex number in standard form. So first, let me remind you that standard form is A plus BI. And what this is your real part or your real number. And the BI here is the imaginary part because it has the I being multiplied by the B value, which also is a real number. All right, so I'm just going to abbreviate because I'm running out of room there. So even if we have a fraction, for example, if we had something such as 3 minus I over 5, that at that point is not standard form because you have to have two very identifiable separate terms, right? Because of this plus sign here. I guess I shouldn't have underlined it because it made it look like it was a subtraction sign. But because of this plus sign here, this indicates that we've got two very distinct separate terms, and if we have a fraction, as we do here in this example that I've drawn here on the side, this is not yet distinct. So we would have to break this up into two fractions, and we could do so by saying 3 over 5 minus I over 5. So that may have been the problem, but if not, I'm going to work on this example that I've written here off to the side. Again, very similar to the problem that the student sent, but let's take a look at it. Okay, so first of all, we notice that under our square root, we have a negative number, right? And we already know that we can't take the square root of a negative number. However, the square root of a negative 1 is I. So if we factor out a negative 1 from the inside, we have a negative 1 times 498, like so. Then there is this rule, it's called the product rule of roots and exponents, that states that if you have these two factors underneath the square root, that is the same as the product of each individual the square root of each individual factor, meaning we can break those up like so. We can pull each factor out and put it under each individual square root and then multiply. So let's do that on this next step. So that was step 2. So let's look at what step 3 looks like. So we have 14 plus, and since we have those two factors underneath the negative 1 and then the 498, we're going to break that up even further, and I'll use different colors here. I'll put the negative 1 in the blue just so you can see that this is the square root of negative 1, and then we're going to multiply by the square root of 498, okay? Because we couldn't simplify that anyhow with that negative 1 under there. We had to pull it out first. So as we're learning in this section, again, I is equal to the square root of a negative 1. So we can now write 14 plus I times the square root of 498. Now normally we put I behind a number, but whenever we have a root symbol or a radicand here, then we actually want to place that in the front, just so there's no confusion on whether the placement is underneath the radical or not. So it just makes life easier. Now I'm going to switch screens here for a moment. Actually, no, let's just stay on the same screen. I'm just going to erase here at the top. I think we've seen this enough. We don't need this information anymore. Well, let me erase. Let's see. Okay. And let's do this one too. Whoa, we don't want to delete all that. Well, okay, I'll switch screens. I'm sorry. Hold on, you guys. Okay, I'm back with you. So what we had left on the other page, we had, again, I'm going to change colors. That pink was a little too much for me. We had 14 plus the square root, plus I, square root of 498 over, I think it was 9, if I recall. Okay, make that a little neater. Okay, so under the square root we have 498, and you may be like, well, I don't know what the square root of 498 is, and that's okay. I don't either, right? But there's a way we can get to it. If you guys may or may not remember, there was something in school when you were in middle or high school called the factor tree. And so what we want to do are determine some factors of 498. Here's a hint. 498, the last number is even. So I know that there's a factor of 2 in there, right? So another little hint is if the last 2 digits are divisible by 4, then the entire number is divisible by 4. And I am doing this in my head, but I'm thinking no, the answer is no, it's not. Yeah, 18 is not divisible by 4. So therefore, let's just try 2 for a moment. Let's just break this down a little bit with 2. 2 times, well, something else I noticed. I think these digits add up to 3. They do. Okay, so if your digits add up to 3, it's also divisible by 3. And since this is divisible by both 3 and 2, then that means it's also divisible by 6. Because 3 times 2 is 6. So actually, let's divide this by 6. Let's make a factor of 6 here and see what we have left, okay? So we have 6. So 6 times what will give us 498? Okay, I'm sorry I don't have a calculator. And I just did it in my head, but I forgot the numbers that quick. I'm sorry. So we've got 8 here, and it looks like we're going to have 18. So 6 and 18 is 3, right? So 83. So 6 times 83. All right. So the idea of the factor tree is that you want to break the number down as far as you can until all you have at your base are prime numbers. Okay. So 6 has factors, has factors of 2 and 3. And 83, let's see. Is 83 prime? I think it might be, but let me try some divisibility rules in my head. And these are just little quick ways to determine how to divide or what factors go into a larger number. So 83 is not even, so I know it's not divisible by 2. So therefore, since it's not divisible by 2, it's neither divisible by any of the other even numbers from 0 to 9. Or 1 to 10 even. Let's just do 1 to 10. It doesn't end in 0, so it's not divisible by 0 or 5. It doesn't end in 5, so it's not divisible by 5. The numbers do not add up to 3 or 9, so it's not divisible by 3, and it's not divisible by 9. Let's see, 7. Let's try, well, we know it's not divisible by 7 because it's not one of the multiples of 7. 7 goes up to quite a large number. 7 times 12, gives you 84. So I'm going to say that this is prime. And therefore we have, whoops, I lost my pen. Therefore we have factored 498 as far as it'll go. Because my base of my tree down here is nothing but prime factors. Okay, so with that being said, what we can do is, well, I'll just back up to this step here, just for purposes of the square root. What you'll notice is that if we use that rule that I gave you earlier, right, that we can split these things up, my question is, does that help you any? If you were to split up those factors of 498 into their own little square root world, if you want to call it. Does that help you any? Does that reduce anything any further? Well, no, it doesn't. But if it had, if say that 6 maybe would have been a 4, then that would have been great because we would have been able to pull something out, right? So with this being said, I made this number up off the top of my head, you guys, so it's probably not a very great example. So I will do another one. But with this being said, really, just to write this number in complex standard form, this number here, this whole thing, in order to write it in complex standard form, all we have to do then at this point is just to break this up into two fractions, where our denominators are the same and the numerators are each go to a individual fraction there. So that's how we would write that one in complex form. Let's take a look at another problem. So I'm going to switch slides again. Okay, so let's take a look at the following problem. Let's look at 3 minus the square root of, let's do, okay, I've got one in my head, 54, that's a 5. My stylus doesn't always pick up very well. Okay, so taking that same approach as before, I'm sorry, there's a negative in there too. I forgot to write my negative. It's a negative 54 under the square root. But taking that same approach as we did before, let's take a look at this problem. We want to know what can we do to write this as a complex number in standard form. So first of all, we want to bring that square root of negative 1 out as an I. So I'm not going to write that step. I'm just going to bring that out. I'm not going to break that down. Leaving us with this, right? Giving us 54 underneath our radicand. So we're going to go to our factor tree. You don't have to do a factor tree, but if you choose to, by all means, please do. So what are some factors of 54 that we know? Well, I know, and I hope you do too, right, that 9 times 6 is 54, right? So if we take and rewrite this as 3 minus I in the square root. So notice underneath what we have at the moment is 9 times 6 all over 4. So again, we can, I'm going to go this way because I'm running out of space. So we can break those up. And what we have now is I times the square root of 9 times the square root of 6. See how that works? All over 4. So once we've done that, we can start a little bit of simplification, right? What is the square root of 9? So we have 3. What we're looking at now is to simplify this one here, if you didn't see what I was doing there. So what we have is 3 minus square root of 9 is 3. So we'll have 3i, right? There's the thing I changed, times the square root of 6. And this is all still over 4. Okay. Now, although I know we didn't finish our factor tree, but something that will help you if you decided to finish your factor tree, you would be able to see where you have those prime factors that repeat to give you a number, so that might help you identify if there's ever one you come across that you don't recognize. Hey, that's a perfect square. 9 is a perfect square, and it's a perfect square of 3, right? So if you didn't know the square root of 9 was 3, breaking your factor tree down to the base of prime factors could help you. Okay, anyway, let's back up, or let's go back to the problem, I should say. So now we're here. And it looks as if we've simplified as far as we can go. And we really have. There's really nothing else we can do. There's nothing under here that will give me a integer or a whole number when I take the square root of 6. So we're done in that sense. but we have not answered the question. The question asks us to write the number as a complex number in standard form. So again, remember standard form is a plus bi. So we have to break this into two fractions. So our denominators are going to be the same on our fractions, and then the numerator goes on each fraction. Those terms in your numerator become the numerators for your fractions. So that would be the final answer, unless there was some simplification that you could do between maybe this coefficient here and your denominator, but in this case there's not. But if you could simplify any of the problems that you come across, please simplify first. So I hope this information was helpful to you. If you have any other questions, please feel free to contact me. Thanks and have a great evening.